Welcome to the deep dive. We take fascinating topics and really try to boil them down to the core insights for you.
That's the plan.
Today, we're venturing into, well, what seems like the abstract world of quantum physics. We're using a discussion with physicist Brian Cox as our guide.
Mm-hmm.
Now, you might be thinking, quantum physics sounds complicated, maybe irrelevant, and honestly, that's exactly the perception we want to tackle today.
Yeah, definitely.
Our mission is to show why this field isn't just for academics and labs, but how it's, increasingly shaping our world and future technologies.
Right.
Think of this as your kind of shortcut, your express route to understanding the key ideas without getting bogged down in maybe decades of historical scientific detours.
Exactly. And the fundamental thing, the really crucial point to grasp right off the bat, is that these quantum rules, they're not some separate physics for tiny things. The quantum world and our big, everyday macroscopic world, they run on the same basic principles. It's just, well, these quantum effects are way more obvious and, frankly, pretty weird from our usual perspective when you look at atoms and, particles.
Weird is a good word for it.
And as Brian Cox really emphasizes, this isn't just theory. It's the bedrock of emerging quantum technologies, stuff that's coming maybe sooner than we think.
Okay, so let's get right to it then. Why should we, busy people, even spend time thinking about quantum physics? Things seem to work okay with classical physics, right? Gravity, motion. What's the big pull towards this quantum stuff?
Well, for one thing, even right now, the meaning of quantum theory, what it tells us about reality itself, it's still being debated. It's not like it's all figured out.
Huh, interesting.
And historically, learning it meant kind of retracing all the initial confusion. The false starts the early pioneers went through. It's like trying to understand your smartphone by first rebuilding the first vacuum tubes. You'd waste a lot of time on dead ends.
So the old way of teaching was basically a history lesson through all the early puzzles.
Pretty much. When Brian Cox was studying, and for a long time before that, the standard way was step-by-step history. The photoelectric effect, why atoms glow certain colors, Bohr's early atom model.
Right.
You'd essentially relive all those head-scratching moments physicists had trying to fit weird observations into the old physics. Think about Rutherford finding the nucleus and that early flawed picture of electrons orbiting like planets.
Which didn't work, right? Because they should lose energy.
Exactly. They should radiate energy and spiral into the nucleus, making atoms collapse. It just didn't hold up.
Wow. Decades of brilliant minds wrestling with this. Sounds like a tough journey.
It was. And learning it that way meant you inherited all that initial confusion. The real leaps forward came with big shifts in thinking. That's why many university courses now often do it differently. They tend to start with where we are now, with our current best understanding of the theory. Lay out the core principles first.
Okay, which brings us to this idea of a qubit, the quantum coin. Can you break that down? How's it different from a regular computer bit, a 0 or a 1?
Right. So a standard bit in your phone, it's strictly a 0 or 1, definite. Like a coin toss landing heads or tails. Done. But a quantum bit, a qubit, think of it as that quantum coin. Yes, when you measure it, you'll get heads or tails, 0 or 1. But before you measure it, it can be in a superposition of both states at the same time.
Superposition. Okay, wait. So it's not just that we don't know if it's heads or tails, it's actually both somehow. That really twists my brain.
It does. It absolutely challenges our everyday intuition. But mathematically, and in countless experiments, it's a proven property of the quantum world. Think of it like, instead of being definitely one thing, it's in a state that's maybe, say, 60% likely to be heads and 40% likely to be tails if you measure it. And the key thing, as Cox points out, this isn't just us being ignorant about its real state. It's a fundamental feature of nature at this scale. It is in that mixed state. And that ability, being 0 and 1, that's what potentially unlocks massive parallel processing power.
Okay, so it's not our lack of info, it's inherent fuzziness until we look. How is that different from, say, predicting rain? We say 70% chance of rain. Is that superposition?
That's a really good question. Gets right to a crucial difference. When we talk about rain probability, it's because the weather system is incredibly complex, right?
Yeah.
We don't know every molecule's position and speed.
Right. Too much data.
Exactly. Our 70% reflects our limited knowledge.
All right.
But deep down, it will either rain or it won't. Classical ignorance. In quantum mechanics, though, the probabilities in superposition, they are the description. That electron in a mixed spin state isn't hiding its true spin. The superposition is its state until measurement forces an outcome. It's a truly probabilistic reality.
My brain is definitely working overtime now. Okay,
Right.
but you mentioned a really key experiment that shows this quantum weirdness, clearly the double-slit experiment. What's that about? Why is it so important?
Ah, yes. The double slit, often called the most beautiful experiment, and for good reason. It perfectly shows this wave-particle duality thing.
Right.
Imagine you have an electron gun, firing electrons, like one by one. They head towards a barrier with two narrow slits in it. Behind that barrier, there's a screen that detects where each electron hits.
Right, so electrons are particles, tiny balls. You'd expect them to go through one slit or the other, hit the screen behind those slits, maybe a bit scattered, but basically two distinct stripes of hits.
Exactly, that's the classical particle prediction.
Yeah.
But that's not what happens.
Uh-oh.
What you actually see on the screen is an interference pattern, a series of alternating bright and dark stripes, places where lots of electrons land, separated by places where almost none land.
Interference, like waves, like water waves going through two openings and making ripples that cross.
Precisely like that. Where wave crests meet, they add up constructive interference, a bright stripe. Where a crest meets a trough, they cancel out destructive interference, a dark stripe.
Electrons. We're firing individual particles. How can particles interfere like waves? It's like throwing baseballs through two windows and seeing a ripple pattern on the back wall.
That's the core mystery. And it gets weirder. Even if you slow it down, send electrons through one at a time. So there's only ever one electron in the setup at any moment.
Yeah.
That interference pattern still builds up over time, electron by electron. It's as if each single electron is somehow going through both slits simultaneously and interfering with itself.
Going through both slits at once. How's that even possible? It feels illogical.
Well, as Brian Cox often explains, drawing heavily on Richard Feynman's work, many physicists would say the electron does explore both paths. In fact, it explores all possible paths from the gun to the screen.
All paths, even crazy zigzag ones.
According to Feynman's formulation, yes, it's not just a way of talking. It's considered a description of reality. For every single path an electron could take, you assign a little mathematical thing called a complex number. Think of it like a tiny clock hand with a length and an angle that spins as it goes along the path.
Okay, a spinning clock hand for every path.
Right. Then, to find the probability of the electron ending up at a specific spot on the screen, you mathematically add up all the clock hands for all the infinite paths leading to that spot.
Add up infinite spinning clocks.
And the length of the final resulting master clock hand tells you the probability of finding the electron there. If the little clocks for different paths end up pointing in similar directions, they add up, make a long final hand, high probability, a bright stripe.
Ah, constructive interference.
Exactly. But if they point in opposite directions, they cancel each other out. The final hand is short, or even zero length slow, or zero probability, a dark stripe. That's the math behind the interference.
So the math works. It predicts perfectly what we see. But what it means about reality, that's still the big question, the
That's so
interpretation.
deep. Does the math just give us predictions, or does it reflect something deeply weird about how the universe actually works? Many physicists think it's the latter. The electron really does explore all possibilities.
Wow, okay. That's a lot to take in. But let's shift gears slightly. You said these weird quantum things aren't just lab curiosities anymore. They're being used in new tech, like quantum computers. How does that work?
Absolutely. Quantum computers aim to harness exactly these principles, superposition, which we talked about, and another crucial quantum thing called entanglement.
Entanglement, right. That's the spooky action at a distance thing. Two particles linked.
Yeah, that's the one Einstein famously worried about. Imagine two particles, maybe electrons, created together in a special entangled state, like a Bell state. Their properties become deeply linked. We'll take spin. We can think of it as up or down. If you have an entangled pair and you measure one electron and find its spin is up, you instantly know the other one's spin must be down, no matter how far apart they are.
Instantly. Even if one's here and the other's on the moon, that sounds like faster than light communication.
It looks like it, and that's what bothered Einstein. He called it spooky action at a distance. It seemed to violate locality, the idea that things are only affected by their immediate surroundings. But experiment after experiment confirms it's real. It's not hidden information. It's a fundamental connection. Though, crucially, you can't use it to send information faster than light. It's more subtle.
Okay, subtle but real. So quantum computers use both superposition qubits being 0 and 1, and this entanglement linking them. How does that give them power?
The power comes from the exponential growth. One qubit in superposition is like holding two states, 0 and 1. Two entangled qubits can hold a superposition of 4 states, 0, 0, 0, 1, 10, 11. 3 qubits hold 8 states. You see the pattern.
It doubles each time. 2 to the power of the number of qubits.
Exactly. So in qubits can represent 2 to the power of n states all at once.
That number gets huge really fast.
Unbelievably fast. Brian Cox uses the example. Just 100 qubits. 2 to the power of 100. That number. It's bigger than the estimated number of atoms in the observable universe.
Whoa.
A classical computer has to check possibilities one by one. A quantum computer, in theory, manipulates all 2100 states simultaneously.
So for certain problems, like maybe simulating complex molecules or breaking codes, it could explore a mind-boggling number of options in parallel. Problems impossible for current supercomputers.
Yeah, that's the promise, exactly. Building stable, large-scale quantum computers is still a massive engineering challenge, don't get me wrong. Dealing with errors, keeping qubits stable, it's hard.
Sure.
But the potential payoff, revolutionizing medicine design, materials science, AI, code breaking, it's why there's such huge investment globally. Imagine simulating drug interactions perfectly or optimizing global logistics instantly. It's transformative potential.
It really sounds like these bizarre quantum rules aren't just abstract puzzles anymore. They're actually the foundation for potentially game-changing future tech.
Precisely. Quantum effects, once thought confined to the micro world, are becoming practical tools. It really highlights that it's all one set of physics rules governing everything, from atoms to us. Their effects are just more dramatic down there.
So to kind of wrap this up, we've seen quantum physics describes this strange reality where particles can be multiple things at once superposition. They act like waves even individually, like in the double-slit experiment. And these rules, plus entanglement, aren't just theory. They're being used to build quantum computers with incredible potential.
Yeah, and it's so important to remember, this weird quantum world isn't separate. Our everyday world, the classical world, emerges from this quantum foundation. It's all connected.
This has been seriously mind-bending. It makes you think, if a single particle really does explore all possibilities at once, what does that do to our simple ideas of cause and effect? Are other solid concepts in our lives maybe more fluid, more interconnected deep down, like the quantum world suggests?
That's the profound question, isn't it? What else might work differently than our intuition tells us?
Definitely something to chew on. Thanks for joining us for this exploration on the Deep Dive.